Oxidation states. Oxidation states are a type of electron bookkeeping. They usually represent very easy marks on the MCAT exam. There are just a few basic rules to remember. The first rule is that all elemental atoms or forms have an oxidation number equal to 0. So that includes things like hydrogen, phosphorus, sulfur. Any elemental atom or form has an oxidation number equal to 0. The second rule, any ion has an oxidation number equal to the charge on the ion. For example, if you have iron, Fe2+, therefore its oxidation number would be equal to +2. Third rule, the oxidation number for oxygen is equal to -2. So this is the oxidation number for oxygen in all compounds except in F2O, which of course you recognize fluorine as being the most electronegative element in the periodic table. Its oxidation number is going to be -1. And so we have -2 for fluorine because -1 times 2. So then the oxidation number for oxygen is +2 in this situation. The other exception are peroxides. And in peroxides, for example, hydrogen peroxide, hydrogen has an oxidation number of +1. So we have +1 times 2, that's +2. So therefore, in order to be neutral, oxygen must have an oxidation number of -1. So those are the exceptions. The fourth rule is that hydrogen has an oxidation number of +1. Once again, there is an exception. The exception is the category of substances called hydrides. For example, sodium hydride. Sodium has an oxidation number of +1. Therefore, to remain neutral, hydrogen has to have an oxidation number of -1. You will recognize hydrides, hopefully, from organic chemistry, or you will, because hydrides are powerful reducing agents. Because of that concept of a hydrogen that has a negative charge that would be very attracted to a partially positively charged carbon nucleus. Of course, that will be discussed in organic chemistry in greater detail. Then there's 5. The fifth and final rule is that the sum of oxidation numbers is going to equal to the charge on the substance. So it equals to the overall charge. So let's look at a couple of examples. For example, H2SO4. So using the rules of oxidation numbers, hydrogen is +1. So this is +2. The oxygen is -2. -2 times 4, that's -8. This substance is neutral. There's no overall charge. So all this needs to equal 0. And sulfur, the oxidation for sulfur is our unknown. So +X. So this is not going to be the most complicated equation you'll have to deal with on the MCAT exam, but clearly 8 goes over to the other side, blah, 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 and then we get X is equal to 6. So the oxidation number for sulfur would be 6. Let's look at another situation, a little bit more complicated, just a little bit. Cr2O7 to the -2. So now we have a situation in which there is an overall charge and it's -2. You may want to pause and calculate what you would provide as the oxidation number for chromium. In order to calculate it, we say -2 for oxygen, -2 times 7, So we have minus 14, and that's going to equal minus 2. So we have chromium minus 14 equals minus 2. We bring the 14 over to the other side. We have Cr2 is equal to 12. So that means that the chromium, 2 chromium, is equal to 12. So chromium is going to equal to 6. So the oxidation number is 6. 3 more points to make about oxidation numbers. The first is that oxidation numbers can change from molecule to molecule. Clearly that is the case, as I've shown these exceptions, but we often see that in substances like sulfur. In different molecules, sulfur can have very different oxidation numbers, so you have to calculate them. So they may vary from molecule to molecule. The second point is that they may be fractions. It is unusual, but if you calculate an oxidation number on the MCAT exam and it ends up being a fraction, the first thing to do is to check your work. Make sure you didn't make a mistake. And if you did go through it properly, then yes, you can have confidence knowing that an oxidation number can be a fraction. And the third point is that the oxidation number is not equal to the valence. Now the valence is what we discussed earlier, which has to do with the outer shell electrons. But the oxidation number that we calculate or develop or memorize, this is not necessarily equal to the valence electrons. Solubility product. The solubility product has to do with weak electrolytes. Many substances, when they're dissolved in water, will ionize. And for example, this is lead chloride, and it produces lead and chloride. Lead, this is Pb2+, and Cl-. 2+, the plus indicating that this is a cation, and Cl- being an anion. Some people remember from high school, it's because anion has An ion, that anions are negative ions. Nonetheless, because these are ions being produced from this solid, the ions can conduct electricity because they're charged. Because they can conduct electricity, they're also called electrolytes. Some substances dissolve readily in water, like strong acids, which we saw before, or NaCl, which is salt, which dissolves into 2 components, which we discussed in terms of colligative properties. Well, lead chloride and many other substances are very weak electrolytes, meaning that they're solid forms, they tend to stay together, and because they tend to stay together, very little will dissolve into water. So because they are weak electrolytes, and because relatively speaking, the amount of the solid form, and sometimes that solid form will be called a precipitate in water, so because the solid form predominates, therefore it is more or less constant compared to the small amount of product being produced. For this reason, there is a constant called Ksp, and that constant refers to the solubility product, meaning the product of the products. So the Ksp expression for this reaction would be just like all the other equilibrium constants, except that we don't have to take the reactant into account because that is more or less constant. So Ksp is given by the product of the products. So we have Pb and we have Cl. Once again, these square brackets representing the concentration, and this is squared because there is a 2 in the equation, in the balanced equation. So we have Pb Cl- squared. So if we're given the concentrations at equilibrium of Pb and Cl, we are able to calculate the solubility product. We expect that the solubility product for a reaction which has a weak electrolyte would be very small, meaning that the KSP would be 10 to the minus something or the other, but it would be a number which is relatively small, 0.00 something or the other. And we expect that because very little product is being produced with these weak electrolytes. We also would expect that the lower the solubility product means the least likely that the substance would dissolve, which means the more likely that the substance would precipitate or to form a solid form when it is in a liquid. The next issue about the solubility product is the word solubility. Sometimes they may ask you about the solubility of a particular substance. The solubility is in moles per liter, and it refers to how much of that substance would actually dissolve. Sometimes solubility is symbolized by S. And if we were to look at this reaction and to talk about the solubility that would occur, then we would symbolize for the lead, we'd symbolize it by S. We'd symbolize the solubility of Cl- as being S, but it would really be 2S, because whatever the solubility of the lead is, there's going to be twice as much of the Cl- being produced because of the stoichiometry of the reaction. So we have 2S. So that when we were to write the KSP expression based on the solubility, this is based on the concentrations, the actual concentrations. But if we were to be asked about the solubility, then we would write S representing the lead, and then that would be multiplied by, for Cl- we would have 2S as being the amount, so we would have 2S squared. So this is KSP would equal to S times 2S squared, and that would be equal to, well, we would have 2 squared, which is 4, and then we have S squared, which is S squared, times S, so that is cubed. So we would get KSP equals to 4S cubed. So if we had to calculate the solubility for the reaction, if we were given the KSP, then we would be able to work it out based on this calculation that the KSP would be equal to 4S cubed, where S is the solubility. Thermochemistry. Thermochemistry is the chemistry of heat changes in chemical reactions. For example, changes in the heat energy or the enthalpy. Now we're going to be looking at this shortly. First of all, there is thermodynamics, which is part of thermochemistry, and we're going to look at thermodynamics separately. There is also Hess's law, which focuses on enthalpy changes in chemical reactions, and we'll be looking at an example of Hess's law and working through a problem shortly as well. And then calorimetry. So calorimetry is actually what we're going to start with. First, we need the tools for calorimetry, and that starts with these two equations. Q is equal to mc delta T, which is definitely these two equations you need to memorize. Some students remember it as Q is equal to mcat. No surprise there. So Q is the heat energy in a chemical reaction. M is the mass. C is a constant, the specific heat capacity, or specific heat. And delta T is the change in temperature. Then we have Q is equal to mL. Q, again, is the heat energy. M is the mass, and L is the latent heat. The latent heat is the energy that flows in or out at constant temperature due to a phase change. A phase change would mean going, for example, from liquid to vapor. That would be a phase change, or vapor to liquid. That would be, so either condensation or vaporization. In this instance, if you're going from liquid to vapor or vapor to liquid, then you would use L sub V, which is the latent heat of vaporization. And that gives information about the energy flow at constant temperature when things are changing phase. So here, this is called the latent heat of fusion. Latent heat of fusion refers to when a substance is changing phase between solid and liquid, or liquid and solid. That's the latent heat of fusion. Generally speaking, of course, the latent heat of fusion is a smaller number compared to the latent heat of vaporization. It takes far more energy to push something up into the vapor phase than it does to change phases between solid and liquid. Now, in terms of using these equations, let's look at an example of calorimetry. So let's do a problem. So here's the question. How many calories are required to heat 10 grams of water from minus 10 degrees Celsius to 120 degrees Celsius? So if you wish, you can pause the video and see if you can develop a strategy as to how this would be calculated. Okay, so let's look at it. Now, there might be a temptation to use Q is equal to MC delta T, thinking that the delta T will take us from minus 10 degrees all the way up to 120 degrees. So we just take delta T, well, that's 130. And M is the mass, so that's 10, we're given that. And C is some constant that they'll give us. Fine, except that's not how it works, because you changed phases twice. You went from solid ice to liquid water, and then from liquid water to vapor. And in each of those cases, you have to stop, and you have to do a calculation at that stage, then continue your calculation, because at a phase change, there will be heat that will be absorbed or released at constant temperature. And that has to be addressed. So to be more specific, if you have solid ice and you start giving it energy, well, the ice will warm up. It will get warmer and warmer and warmer until it gets to 0 degrees Celsius. Then you'll continue to give it energy, but the ice is no longer warming up. Rather, it is changing phase. So the ice will turn into liquid water at 0 degrees. Even though you're increasing the amount of energy you're giving it, the temperature is not increasing. The only thing that's happening is you're getting a phase change. Then, once it has become liquid water at 0 degrees Celsius, then the energy that you're providing will now start warming up the liquid water to 10 degrees, 20 degrees, 50, 60, 80, 90, 100. Now you continue to give energy, and the temperature is no longer increasing. It stopped at 100, because now all the energy that you're providing is going into changing phase. That's a latent heat of vaporization. So the liquid water at 100 degrees is turning into vapor at 100 degrees. And once you have vapor at 100 degrees, then the energy that you're providing will now increase the temperature of the vapor from 100 degrees, say, to, for example, to 120. So with that concept in mind, now it's easy to calculate. So we'll just go over the basic ideas of the calculation. So to start with, we want to warm up the sub-zero ice from minus 10 to 0 degrees. So to do that, we use Q is equal to MC delta T. M is 10. C is a constant which you will be given, which is 1/2. It's 1/2 for solid water or ice, and it's about 1/2 as well for vapor. And then we have delta T, which is change in temperature. So M is 10, change in temperature is 10, so that's 100, and C is 1/2, so that's 50. So it takes 50 calories of energy to warm up the sub-zero ice. Then, when we have ice at 0 degrees Celsius, we have to calculate how much energy is required to change that ice to liquid water at 0 degrees Celsius. To do that, we use Q is equal to mL, because there's no change in temperature. So M is the mass at 10. L is the latent heat of fusion. The latent heat of fusion for water is 80 calories per degree Celsius. Calories per gram. So, but you don't need to memorize that, okay? You don't need to memorize that number at all. It's a constant. It will be provided to you if they ask you this question on the MCAT. So this is 80, that's 10, so that's 800 calories. Imagine, it only took us 50 calories to warm up the sub-zero ice, but 800 calories in order to change its form from ice to liquid water at 0 degrees without any change in temperature. Now let's take the 10 grams of liquid water at 0 degrees and warm it up. Now as we warm it up, we can only warm it up to 100 degrees Celsius. It can't go to 120 because there's a phase change at 100. So we use Q is equal to mc delta T to get it up to 100 degrees. So delta T will be 100. M is 10, so that's 1,000. And C, a constant for the liquid water, is 1. So we get 1,000. So the energy will be 1,000 calories, or 1 kilocalorie. So far we have to add the energy for each step. We have to add 50 calories to the next step that we got 800 calories, then we got 1,000 calories. So we have to add up all the energies to get the total energy required to go from minus 10 to 120 degrees Celsius. Just a little aside. Usually when a constant is equal to 1, you should memorize it. You probably memorized already the density of water is 1 gram per cubic centimeter or 1 gram per milliliter, whatever way you want to memorize it. Or 1,000 kilograms per meter cubed. That's also an important one. But the C specific heat for liquid water being 1 makes sense because the definition of a calorie is the energy required in order to heat up 1 gram of water 1 degree Celsius. So the idea that specific heat would end up being equal to 1 calorie per gram per degree Celsius is no surprise. Anyway, so what do we have? We have 10 grams of liquid water at 100 degrees Celsius. So now we continue to give it energy, and all the energy is not going into changing temperature, it's going into changing phase. So we're going from liquid water to vapor. So in order to do this, we can't use this. There's no change in temperature. We have to use Q is equal to mL. And for the L, this time it's the latent heat of vaporization, which happens to be 540 for water. So we have the M is the mass, which is 10 grams. LV is 540, so we have 5,400 calories, and so on. And then for the vapor, we do the same thing, going from 100 degrees Celsius up to 120 degrees Celsius. So that would be a delta T of 20. C, as I mentioned before, for vapor is 1/2. Then we have 10. So we have 100. Then we add up all the different levels of calories, and therefore we have the total energy required in order to do this reaction. But in order to do it, we had to do it in stages in order to respect the fact that water will change phases at certain temperatures. We are now going to look at the laws of thermodynamics. To begin with, this one is very, very simple. If you have a system A that is in thermal equilibrium with system B, and if B is in thermal equilibrium with system C, guess what? So from simple logic, it means that system A is in thermal equilibrium with system C. What's the big deal? Well, that's the basis of a thermometer, for example. A thermometer takes the temperature of one person, for example, and if the temperature is 38 degrees Celsius, which is a little high, and then the thermometer takes the temperature of someone else and it's 38 degrees Celsius, well then that means that A and C have the same temperature. So they're at thermal equilibrium with each other, so they're both at the same temperature. This is called the 0th law of thermodynamics. Yes, indeed, it was thought of after the first law of thermodynamics, and it was determined to be more fundamental than the first law of thermodynamics. So this is number 0, okay, in the list. So next on the list is the first law of thermodynamics. And the first law of thermodynamics states that any change in internal energy of a system is equal to the heat of the system minus any work done. So this would be the heat added, for example, minus any work done by the system on its surroundings. And finally, the second law of thermodynamics, which is the most popular law of thermodynamics, which we looked at in physics, in the context of physics, but in the context of chemistry. The second law of thermodynamics refers to the fact that spontaneous reactions tend towards increased entropy. Entropy is a measure of randomness or disorder. On a growth scale, for example, in chemistry, going from solid, which is, could be a crystalline solid form, to liquid would be an increase in randomness or disorder, because crystalline is very solid, very ordered, and so it has very low entropy. But then liquid form has molecules moving around, a little bit more disorder, and then going from liquid to the vapor phase, where molecules are just, jetting out in all different directions and bouncing about. That's a lot of randomness. So that's a tremendous increase in entropy going into the vapor phase. So that is the concept of entropy. Now, it is often calculated by using the following equation, and this is a term called Gibbs free energy, and this is going to allow us to determine whether or not a reaction is spontaneous or not. So Gibbs free energy, delta G, is equal to the enthalpy, delta H, minus T, the temperature, and delta S, which is the change in entropy. So it is a measure of entropy. So one would expect that the higher the entropy is the more likely that there will be a spontaneous reaction. And this, of course, is the case. Now, on the MCAT, they don't generally require you to memorize either of these equations or to calculate on the basis of these equations unless they provide the equation in the passage. However, what they will do is they'll ask you whether or not a reaction is spontaneous or not, depending on the delta G value. In other words, depending on the Gibbs free energy. So the bottom line is as follows. If delta G is negative, then the reaction is spontaneous. No surprise there, because if delta G is negative, likely delta S, the entropy, was very high to create a negative value on the right side of the equation. If delta G is positive, then the reaction is non-spontaneous. And if delta G is equal to 0, the reaction is in equilibrium. Hess's law. Hess's law refers to certain manipulations that can be done concerning heats of reaction. You have to imagine that in chemistry, many different types of reactions can occur. Associated with these reactions are certain changes in terms of energy or heat that may evolve from the reaction or may be required for the reaction to occur. The changes in these heats that of the reaction is the delta H of the reaction. We mentioned before that if energy or heat leaves the reaction, is released from the reaction, that's an exothermic reaction. And if energy or heat is required for the reaction to occur, that is an endothermic reaction. The delta H for an endothermic reaction is positive. The delta H for an exothermic reaction is negative. Because these different chemical reactions have different delta H's, but the delta H's are always dependent upon the initial and final circumstance of the reaction, they are called state functions. That means it doesn't matter how the reaction occurred, it doesn't matter what happened in between the final and initial circumstance for the reaction. It only depends on the heats initially and finally, and that provides us with our delta H for the reaction. So both chemical reactions and the formation of chemicals have heats associated with them. The formation of a chemical will have a heat associated, and that would be called delta HF, or the heat of formation of that chemical. Hess's law comes from the fact that delta H, or heats of reaction, are state functions. And because they're state functions and they only rely on the final and initial circumstance of the situation, then we can do certain manipulations. For example, if you were given a reaction and you were given the heats of formation of the chemicals in that reaction, using Hess's law, all you would need to do is take the sum of the heats of formation of the products, subtract the sum of the heats of formation of the reactants, and you would have the overall delta H of the reaction. So these reactions have delta H's associated with them. Here, this reaction has delta H1. This reaction here with calcium hydroxide has delta H2. Now let's say that you were provided these two reactions and you were provided with the actual values of their delta H. Then you were provided with another reaction and were asked, what is the delta H of this reaction based on your knowledge of the delta H of these other two reactions? You may want to consider how you would respond to that. So you may want to pause now. Well, the way you would do this is you would line up the equations that you were given with the equation that you want. So we have 2H2 here. Well, that's also on the left side. We have oxygen on the left side. That's also on the left side. And we have water. So water is not there. So water has been eliminated somehow. But the rest of the equation lines up exactly like this. So we're not going to alter the way the first equation is written. Now the second equation, we have calcium hydroxide on the left side. But over here we have calcium hydroxide on the right side. Furthermore, we have 2 times it. Then we have calcium oxide, which is on the left side. So clearly we're going to have to switch the equation around. And we're going to have to multiply this equation by 2. And that seems to work out quite nicely, because then we'll have 2 times water. And when we switch this over to the other side, and we have 2 times water on the left-hand side, we have 2 times water on the right-hand side of this equation. So when we add up the equations, we would be able to cancel the 2 times water from the both sides. Then we would end up with exactly this equation. So the only manipulation we would need to do before we add these 2 equations is we would need to flip this over, which is to invert the equation, and we would need to multiply through by 2. To invert the equation, we therefore would turn this delta H2 into negative delta H2, and then to multiply it, the equation through by 2, we also multiply the delta H2 by 2. In other words, the delta H for the given reaction, the total delta H, or enthalpy, for the given reaction would be given by delta H1, because that reaction was not changed, minus 2 times the value for delta H2. And this would give the overall enthalpy for the final reaction. We will now examine the rate law. The rate law refers to the rates of reactions. Now you could consider the rate of reaction sort of like the speed at which the reaction occurs. Normally when you think of speed, you might think of miles per hour or meters per second. But in a chemical reaction, because they are chemicals, we are really talking about the concentration per second. In other words, moles per liter per second. That represents the rate of the reaction. Now here is a typical reaction. So we have reactants, say A and B, whatever they may be, and then producing certain products. Now we can write the rate law for the reaction. The rate law is that the rate of the reaction in moles per liter per second is equal to the rate constant K times the concentration of the reactant A times the concentration of the reactant B. Now each reactant is raised to a power. The exponents are not necessarily equal to the stoichiometric coefficients. Because if you look at this reaction, clearly the stoichiometric coefficient for A must be 1, and the stoichiometric coefficient for B also must be 1. And so it is not necessarily the case that X and Y must equal 1, because in the balanced equation, the stoichiometric coefficients equaled something in particular. You can't make that assumption. What you need to do is, in order to determine what the exponents are, you have to examine a particular experiment. Then by looking at the experiment, you can determine what the exponents must be. For example, in this experiment, you examine what the initial concentration and initial rates of reactions are, and then by examining the rate law, we will be able to determine what the exponents must be. So, in order to do so, we look at an experiment in which one of the particular reactants will not change. Then we look at what happens when the other reactant does change, and we examine its effect on the rate of reaction. So if we look at the first two experiments, in the first two experiments, the concentration of A remains constant. It is 0.10 moles per liter, and then it is 0.10 moles per liter. So it does not change in the first two experiments. Now in the first two experiments, the concentration of B doubles. It goes from 0.10 to 0.20. Now we have to examine what is the effect of doubling B while A is constant. What is the effect of doubling B on the rate of the reaction? Well, the rate of the reaction goes from 1.23 times 10 to the minus 3 up to 2.46 times 10 to the minus 3. So it doubles. Doubling B leads to doubling of the rate of the reaction. So if B doubles, if you have 2 times B, you end up with 2 times the rate of reaction. So it's a perfect 1-to-1 ratio in terms of what happens. In terms of having a factor of B, you have the same factor for the rate of the reaction. Therefore, the exponent for B must be equal to 1. So we've worked out what the exponent of B must be because we were able to keep A constant and see how the rate of the reaction would change as B changes. Now, let's keep B constant, change A, and see what effect it will have on the rate of the reaction. So A changes when we compare experiment 1 and experiment 3. We go from 0.10 up to 0.20. So we doubled the concentration of A. B remains the same, 0.10 to 0.10. So while B remains the same, we double A. Let's see the effect on the rate of the reaction. The rate of the reaction goes from 1.23 times 10 to the minus 3 up to 4.92 times 10 to the minus 3. In other words, the rate of the reaction quadruples. It is 4 times. So we double A, we get 4 times the rate. So if we add 2A, something happens with this exponent to make it 4 times. Clearly, x must be equal to 2. So we have x is equal to 2. And that means 2A, the 2 is squared, making 4, and therefore we have 4 times the rate. Now we can see how you would develop the exponent for any kind of reaction that they would provide. We've now noted that it's 2 for A and 1 for B. There's other ways of saying this. The most common way of saying it is that the rate of reaction with respect to A is second order. The rate of the reaction with respect to B is first order. So you can talk about the individual components and what the rate of the reaction would be with respect to that component, and that is equal to its exponent. If you want to talk about the overall rate of the reaction, then the overall rate of the reaction will be the sum of the exponents. So it would be 2 plus 1. The overall rate of the reaction would be third order. It's a third order reaction. This concept of the order of reaction will also come up later when we look at organic chemistry. Now, a couple of other things to note about this. 1, imagine what you would give as a response if you changed the concentration of A, you doubled A, but the rate of the reaction didn't change. You tripled A, the rate of the reaction didn't change. Whatever you did at A, the rate of the reaction didn't change. What would you consider to be the order of the reaction with respect to A? You may want to pause and consider your response. Well, the order of the reaction would be 0. The exponent would be 0, because no matter what you do with A, it doesn't affect the rate of the reaction. So you would say that the rate of the reaction is 0 order with respect to A. But in terms of the overall rate of the reaction, once again, you would add up all the exponents, whatever they may be, and that would give you the overall rate of the reaction. So that's one point. The other point is, be careful on the MCAT exam with your exponents. Now here, they are all 10 to the minus 3. But they might put one of the exponents as 10 to the minus 4 or something like that. They'll do that very commonly on tables, whether it be for general chemistry or any of the basic sciences. The important thing for you to do, just to keep everything consistent in your table, just cross out whatever they have which is different and rewrite it on the side in a way which is consistent with the rest of the table so that you don't make any mental errors. So for example, if 1.23 was 10 to the minus 4, then in order to make that 10 to the minus 3 like the others, we would just write 0.123 times 10 to the minus 3. Some students like to remember that if you add a number up here, then you subtract a particular part of the decimal. You move the decimal more to the left. And if you subtract a number from here, say you add minus 1, then you move the decimal to the right. So if you have 10 to the minus 4, then it's like moving the decimal to the right. So 12.3 times 10 to the minus 4 would be equivalent to 1.23 times 10 to the minus 3. That kind of comfort with exponents is important for the MCAT exam. Well, we've looked at reactions and the rate of reactions. We also know that associated with reactions is a change of energy or a change of heat, which we call delta H, the enthalpy. And this produces reactions which can be endothermic or exothermic. The next thing that we will look at are the potential energy diagrams that are relative to this particular endothermic or exothermic reactions. You are now looking at potential energy diagrams. Now consider the complicated chemical reaction. A plus B goes to C plus D. Therefore, A plus B would be our reactants, and C plus D would be our products. Now, of course, there are changes in energy during reactions. And so consider these two different possibilities. To begin with, we start with a particular energy for our reactants. We end off with a particular energy for our products. So in one possibility, the energy of our products is much lower than the energy for the reactants. So here's the reaction progress, meaning as the reaction is occurring, there is a change in energy. The change here is that A plus B has much more, the reactants have much more than the products. So therefore, energy must have been released in the reaction. If energy is released or energy exits a reaction, we call that an exothermic reaction. And that means that the delta H for the reaction, the enthalpy for the reaction, would be negative. So if you were to look at the difference between the energy of the reactants and the products, well, that would be about like this. That would represent our delta H for the reaction. So that's the delta H, which would be the difference of the energy of the reactants and the products. And in this particular case, this is clearly an exothermic reaction because the products have less energy, which means that energy must have been released in the reaction. Therefore, delta H must be negative. If you have difficulty remembering that delta H must be negative in this type of reaction, remember that the delta H will be calculated by the total energy of the products minus the total energy of the reactants. So I don't know what the energy of either is, but I do know that the energy of the reactants is clearly here higher than the energy of the products. So if you had products minus reactants and the reactants is a larger number, then you end up with a negative number. So the delta H here would be negative. In this particular reaction, we start off with a low energy for our reactants. We end up with a higher energy for the products. So in other words, energy was gained. Energy must have been added for this reaction to occur. That is an endothermic reaction. That means that the delta H must be positive. And the delta H would be, of course, here, would be the difference between the reactant's energy and the product's energy. So this would be the delta H of this reaction. Now the reaction sort of, during the reaction progress, as it's proceeding, sort of goes up into this lump and then it comes back down. Well, this area up here is what is called the activated complex. In organic chemistry, we more commonly call it the transition state. This is the time and place where the bonds are being created and broken in order to make the new products, because these A and B is going to react together, and therefore there's going to be new bonds that are being created and destroyed and so on. And so this is occurring at the activated complex at the top of the curve, both here and both here. And then we get the particular products being formed. Now, the difference in energy between the reactants and the activated complex is called the activation energy. So that's between here and here. This is the activation energy, and it is symbolized by an E with a small letter A, a subscript A. That's the activation energy here. And so it is a difference of energy between the activated complex and the reactants. So here's EA for this reaction. When you have a small EA, it is more likely that the reaction will occur spontaneously. When you have a large EA, it is unlikely that the reaction will occur spontaneously. So here is a reaction. We know we start with a high energy, we end up with a low energy. Energy is released. It is more likely that this will occur spontaneously with its low activation energy than this reaction with this huge activation energy. In order to get over this mountain or lump or hill, it would be very difficult, if not impossible, for this to occur spontaneously at least. So it would require energy to help bring it over into the products. Now there are ways that the activation energy can be reduced. In particular, a catalyst is a compound that could be added to a reaction. It won't be used up in the reaction, meaning it is regenerated at the end of the reaction, yet it increases the rate of the reaction. The reaction will occur faster by using the catalyst. The catalyst will indeed reduce the activation energy. There might be a series of steps, but each step will have a lower activation energy overall in order to produce the products. So in summary, if you were to compare this particular curve to what effect a catalyst would have on it, well, what it would do is that you would start here with your reactants, and then the catalyst would create a curve something like this, so that the activation energy would be lower. The activated complex will be in a lower position, a lower energetic position because of the use of the catalyst, and therefore the activation energy will be lower. So these are common curves that you may see on the MCAT exam, so it's important to quickly recognize them and to know what your delta H is, your activation energy is, and the particular effect that a catalyst can have on these curves. Now we're going to move on to electrochemistry, and in particular, electrolysis. Electrolysis. If you open your mind to electrochemistry, you'll find that it is a very straightforward subject. Here we have a battery. It is connected by some wires to electrodes. These electrodes are in some sort of fluid. Now let's say that that fluid was molten salt, meaning that it's Na plus and Cl minus in solution only. So all we have is Na plus and Cl minus in solution. Then we have these electrodes, and these electrodes are, say for example, an inert substance like platinum, so that the electrodes are not going to get involved in the reaction. So we're going to be looking at what happens to NaCl as a result of having these electrodes here. Then we have the battery, and you may remember from physics that as soon as you see a battery, your Pavlovian reaction is to look at the large electrode and to label that as positive, and to look at the smaller electrode and label that as negative. So this is the positive electrode, and this, because there are electrons emanating from this terminal of the battery, this would be negative. So the battery is going to result in a charge difference in the electrodes. So that's fine. Now in solution, we have Na plus and Cl minus. Well, imagine that because electrons are flowing into this electrode, making this electrode more and more negative, sodium, which is positively charged, is going to be attracted to the electrode, which is negatively charged. Chloride, which is negatively charged, will be attracted to the electrode, which is positively charged. Now the word electrolysis. You may remember from biology that the word lysis often refers to something which is being split apart. Well, electrolysis is the word, and the reason is because the battery is providing electrons and creates a charge difference. That's the electro part. The lysis is the fact that before the charge went to the electrodes, sodium and chloride were just hanging around in solution, kind of ionically bonding. And so sodium and chloride was involved in an ionic bond, very relaxed, nothing special going on. But as soon as these powerful charges come in to the electrodes, then the sodium and chloride atoms that were being bonded ionically suddenly are being torn apart separated such that the negatively charged chloride goes to the positive electrode and the positively charged sodium goes to the negative electrode. So this is electrolysis. Now, there is a mnemonic that you can memorize that will help you remember where the anode and cathode are. That mnemonic is Leo is a jerk. I suppose this would be more correctly pronounced Gurk, but that's not a great mnemonic. Anyway, so Leo is a jerk, and that stands for loss of electrons, oxidation is anode. Gain electrons, reduction, cathode. So as sodium comes here to this electrode, what's going to happen? Well, the Na plus is going to gain an electron, so plus an electron, and that's going to give us sodium, which is solid. So you literally have the cation, sodium, coming to the electrode, gaining an electron, and because it gains an electron, because sodium now becomes solid, it plates onto the electrode. It just literally becomes solid right onto the electrode. So this reaction, because it's a gain of electrons, that means sodium is being reduced, and that means that this is occurring at the cathode. So this half reaction, it's called a half reaction because it's only part of the reaction that is occurring. This half reaction is at the cathode. Let's look at the other side. Cl minus is being attracted to the positive electrode. When Cl minus goes to the positive electrode, it gives up its electron. All this based on opposites attract. So Cl minus goes to the other electrode. It gives up its electron, and so it's going to become chlorine, Cl2. So this is going to be actually 2 Cl minus, and that's going to give 2 electrons, and that provides us Cl2, which we know is a gas. So in other words, because it provides Cl2, we know that at this electrode, chlorine will bubble out as a gas, and at this electrode, sodium will be plating onto the electrode. So when we do these reactions, these are half reactions, we want them to balance. We want the electrons to cancel. So we multiply through here by 2. Then we add the reactions, and then we end up with 2 Na plus 2 Cl minus, giving us 2 Na plus the chlorine gas, which is released. So now we have clear what our cathode and our anode, where they are, why this occurs, and it also provides interesting information about the idea of electrolysis. You can imagine what a wonderful invention this was in order to save industry money, because beforehand, if you needed to have a gold-plated jewelry, for example, someone would literally melt the gold and paint it onto the piece of metal. And so you would have millions of atomic layers of gold onto that substance. Well, could you imagine how much industry could save if they could take gold, which is Au2+, put gold into solution, and then create a negative electrode out of the metal or jewelry, and then let the gold ions just plate onto the jewelry to the point that it just looks gold. And then they sell that to you, and it lasts a few months. But you could imagine that by doing this, you can just put a minimal number of layers of atomic gold rather than millions of layers, and it would save a tremendous amount of money for them, of course. Nonetheless, let's move on to another slightly more complicated electrochemical cell. This is an electrochemical cell. Notice the highlights. To begin with, this is a zinc electrode. So it is made out of zinc, solid zinc. This is a copper electrode made out of solid copper. Here is a wire connecting the two. This is a voltmeter, meaning all it is, it doesn't drive, it doesn't give energy, it's not a battery. All it is it tells us how much voltage there is in the system. So it just provides a number. And then we have two containers with fluid. This container has zinc sulfate. This container has copper sulfate. Both of these are containers that contain water, so this is zinc sulfate aqueous, meaning it is an electrolyte, and so it will dissociate. So zinc sulfate really means to us that there is Zn2 plus and SO4 double minus floating around in solution. And here the same, there is copper 2 plus and sulfate double minus that are floating around in solution. This part of the electrochemical cell is called the salt bridge. In it, there are ions of salt. There's Na plus and Cl minus in the salt bridge. Thus, they can move from one container to another. This cell, which is called an electrochemical cell, is also called a galvanic cell. Now, you just have to take one thing for granted from me, and then after that, everything just sort of flows from that one point. And that is that if you were to hook up zinc to copper, it so happens that zinc has a tendency to give electrons compared to copper, and copper has a tendency to receive electrons compared to zinc. Therefore, just hooking the system up leads to electrons leaving the zinc, attracted to the copper, going through this system, and we'll discuss later how you can know this, but nonetheless, the electrons are passing away from the zinc, so we have electrons moving in this direction, electrons moving along here, electrons moving into this electrode. So this electrode will become negatively charged. Now, as a result of the fact that this electron is becoming negatively charged, and in the presence of copper sulfate, meaning Cu2 plus in solution, the Cu2 plus in solution will become attracted to the negatively charged electrode, and it will plate onto the electrode. It will become solid. So in other words, we have Cu2 plus electrons, 2 electrons, will give us Cu solid. So copper solid is being produced here because there's a gain of electrons. Therefore, copper is being reduced, and this is occurring at the cathode, given by Leo as a jerk. So we have copper, which is plating on to the electrode. But something's wrong with this picture. And that is that there was balance. It was a solution that had ions in it, but there was an equal amount of ions, cations and anions. So now that copper is plating onto the electrode, then the balance is disrupted. The overall charge of the container will start to become negative, because as the Cu2 plus plates on, then you're going to have a net SO4 double minus just hanging in solution. Well, you've never been to a chemistry lab and created a cup full of positive ions or a cup full of negative ions. It would always be balanced. It takes an extraordinary amount of energy in order to produce a container filled with one or the other charges. So This would not occur, certainly not spontaneously as it is happening here. Therefore, in order for this reaction to continue, in order to make sure that it's not going to just stop, you need a salt bridge. And the reason is because in here we have Na plus, in the bridge there's Na plus and there's Cl minus inside of the bridge. So as you start getting a net SO4 double minus here, the sodium in the salt bridge will start to race in to the solution on the right side. In other words, it helps to maintain neutrality. That's one of the objectives of this salt bridge, to maintain neutrality. Instead of having a cup full of negative ions, which wouldn't happen anyway, but in order for the reaction to continue, the sodium comes flying in here and rescues the situation. Now let's go on to the other side. The zinc is giving up electrons to the copper. Every time the zinc gives up electrons, releases electrons, the solid zinc in the electrode becomes Zn2+, because it gave up electrons. So it becomes Zn2+, and therefore it falls into solution. Well, once again, you can't have a container with a net positive charge in it created spontaneously. So as it falls into solution, creating a net Zn2+ in the solution, Cl- from the salt bridge comes down and rescues the situation and helps to bring back balance of charge or neutrality in the container. So the salt bridge does two things. One, it helps to maintain neutrality. And the second thing the salt bridge does is it completes the circuit. After all, watch the flow of negative charges. Zn giving up electrons, falling into solution. So we have negative charges here flowing through the wire. Negative charge, 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 and then through the salt bridge. Negative charge, negative charge, negative charge, negative charge. And so the circuit is completed by the movement of charges because there's the presence of the salt bridge. Now you know why this is called an electrochemical cell. Here, the electrons carry the charge, and here the chemicals carry the charge. Electrochemical cell. It's also called a galvanic cell, and after all, this is the basis of modern day batteries. A couple of more points. First, the half reaction of the zinc. So we looked at the copper half reaction. The half reaction of the zinc would be Zn solid going to Zn 2+ plus 2 electrons. This is a loss of electrons, therefore it's being oxidized. Loss of electrons, oxidation is the anode. So if you were to add the half reactions, you would get Cu2+ plus Zn, giving us, because the electrons would cancel, that gives us copper solid plus Zn2+. So I have a question for you. Why is it that an electrolytic cell and an electrochemical cell are opposites? You may want to pause and consider your response. The reason is, in an electrolytic cell, we saw that we put a battery there. Then the battery pushed charges into the system, and then it broke apart the chemical. So an electrochemical cell requires energy, a battery, whereas a galvanic cell or electrochemical cell is a spontaneous reaction. This occurs spontaneously, therefore it actually is a battery. It does not require a battery in order for this reaction to occur. So that brings up the point of why is it that zinc was able to do this? Well, there are certain tables that would be provided to you that are called reduction potential tables. And what those tables show are reactions as reductions. So they will show a reaction like this as a gain of electrons. Then that reaction would have a value, a potential associated with it, and it's called the E0 value. This potential, this reduction potential value, the 0 represents it is at standard conditions. That is important for the following reason. Because it's standard conditions and that the concentrations are standardized, if you were to multiply your reaction through by any kind of coefficient, like we did before, where we multiplied through in order to get 2 electrons to balance our equation, you do not multiply the E0 value by a number because the concentrations are standardized. It is not like enthalpy, delta H, where when you multiply through by a particular stoichiometric coefficient, you must also multiply your delta H value by that number. But here, if you multiply through, you do not multiply the E0 value because the concentration is already standardized. So that's one important point. The other thing is that they're all written as reductions in these reduction potential tables. The way it works is that the E0 value, which is most positive, is the E0 value which is most likely to occur spontaneously. If you have a negative E0 value, you do not expect that that would occur spontaneously. So when you switch your reaction around, like zinc has been switched around, it's not written as a reduction, it's written as an oxidation. So when you switch the reaction around, you change the E0 value from positive to negative, or from negative to positive. And then when you add 2 equations, then you just add your 2 E0 values to get the final E0 value of the reaction. Clearly, the final E0 value of a reaction like this would be positive because I've already mentioned that this is a spontaneous reaction.